Welcome to Calculus. Today, we will investigate finding limits of functions numerically in a table and graphically on a coordinate plane. Let's take a look at two examples. We'll have a total of four, but let's start with two examples. So I'm going to head to the notes screen. So here we are with our initial limit. So we'll read the instructions here. It says evaluate the limit by creating a table of coordinate points and graphing the function. If the limit does not exist, give a reason why it does not. So let's begin by graphing this function. We're going to treat this, like I'm saying, as a function. So really what we're looking at is f of x equals this x minus 2 over x squared plus x minus 6. And we want to create a visual graph. So I just want to sketch it here. I'm creating a coordinate plane. And to do so, we're going to look at the values in a coordinate plane table. So traditionally, we would use -2 through 2 for our domain, but let's wait and see what the graph looks like. So I do want to initially just graph this on the graphing calculator. So I'm going to head over with this function in tow to Desmos, and I just want to type it in as we wrote it. Now I'm going to look for a table of values so that I can plot this myself. So recall in Desmos, you do need to put parentheses around the numerator. And then for the denominator, x squared plus x minus 6. And that gives us a nice graph initially of this function. Definitely we're looking at a rational function. And it appears that we've got a vertical asymptote over here at x equals -3. So I want to create a graph of this on our note screen. So to do so, I'm going to click that cog, and I'm then going to select here in the function entry line, convert to table. And there's our -2 through 2. Now I did pause because I want to back up. I want to catch that window where we've got the vertical asymptote. So I think it's at -3, and Desmos is confirming that by giving the output undefined. And I also see I got something undefined here at 2. So I'm going to extend my table past. So I'm going to copy these values down. So at -4, I'm at -1. And then past -3, all the values flip up over the x-axis, so +1. And then decreasing down towards the x-axis, 0.5, point repeating 3, point quarter. We do have an undefined value. We'll have to deal with that for our limit. And then 0.1 repeating 6 is past that. Well, we have what we need from our calculator. So let's head back to our coordinate plane and let's recreate that table and that graph. So again, we had extended this back to -4, and we'd gone all the way to +3. So I'll write those values in. And then the output values are -1. At -3 was undefined. -2 was 1, 0.5, point repeating 3s, 0.25, another undefined value, and then 0.1 repeating 6s. So we'll graph that here. I'm going to head out 4 in the left direction. So that one's down at -1, quadrant 3 there. There's a vertical asymptote. That's the undefined part here at -3. And then past -3, -2 bumps up to +1. -1 was at half. 0 was a third. 1 was a quarter. 2 is undefined. We can go ahead and say what that's going to look like on the graph. That's what we would call a point discontinuity. It's a hole in the graph. Later on, we'll see algebraically why does that occur. But for now, we just see it's in line with that right-hand curve, but it's undefined. And then 3, we can kind of see why it's undefined. It is in line there. It's just not showing up on the graph. So we'll sketch this graph in. So there's that left branch of the rational function. And then here's the right branch. And we've finished that first task. We have graphed the function from a table of coordinate points. Now, our goal isn't just to graph this function. It really is to find the limit as x approaches 2. Now, we've seen that there's something unusual going on there. So if I look as the x values come over here from the left to the right, and the same from the right to the left, I see that they're coming to the same y value. So that means for us that the limit exists. What we need to do is figure out what would this value have been at 2 if it hadn't fallen out of the function. So something happened algebraically, but our goal in this segment is really to see, can I figure out what that value would be roughly from a graph, and then more specifically from a table. So we know it's kind of going to fall in between 0.25 and 0.1 repeating sixes. So the question is, like, how can we actually find a number? Now, a way we can do that is to create a more refined table of values. So what I'm going to set up, this will be a horizontal table. I'm going to put my x's in the top row, and I want to center around 2. Now, at 2, we already know that the output for the function is undefined. So I'm going to write that down below. The output is undefined at 2. So if I were to try what we had looked at first with direct substitution, it wouldn't have worked. I put 2 in there, and really what it's going to create in the denominator, well, let's go ahead and see what that's going to do. So f at 2, I'm going to just substitute 2 for all the x's. So that's 2 minus 2 for the numerator over 2 squared plus 2 minus 6. Well, in the numerator, I've got 0. That's okay. That wouldn't have been a problem. But in the denominator, when I do 2 squared, that's 4 plus 2 is 6 minus 6 is also 0. And we're not permitted to divide by 0, and that's why it's bumping out on the calculator as undefined. This is what we call an indeterminate form. So direct substitution's good, but sometimes it yields this indeterminate form, and we have to have another strategy in order to calculate or evaluate the limit. So from a table point of view, what I want to do is get really close to 2. So the way that I would do so is really by saying, what would be the output at 1.99? And then I can kind of investigate here, what would be the output at 1.9? In fact, let's make this even closer. Let's go 1.999, 1.99, and then we'll also find 1.9. So we're going to find 3 values there on the left. Now I want to see what are the values on the right as well. So I'm going to go 2.001, 2.01, and then 2.1. So I want to fill out that table. Now we could do that manually, but we do have tools at the ready. So I'm going to head back to Desmos. And what I want to do is I'm going to work with, in fact, I'm going to get rid of this table, and I want to create a fresh table. And I'm going to put those values here instead of -2 through 2. I'm going to start with 1.9, and then I'm going to hit enter and type in the other values we had put in our horizontal table. So 1.99, and then 1.9. 0.999. And then we want to put the 2 right there. Remember that was undefined. And then 2.001, 2.01, and then 2.1. We can clear out that last one. So I'm going to record these values, and what we're looking for is, as we get real close to 2, can we predict what that number would be if it hadn't fallen out of the function? So at 1.9, in fact, let me record this real quickly. So it's 0.204. At 0.99 is 0.200. 1.999 is 0.20004, but I'm going to stop at the nearest thousandth. 2 we saw was undefined. 2.01 is 0.1999. So I would round up to 0.200. 0.199 again, 0.200 if I round, and 0.196. So I'm going to head back. We got the information that we need here. So just notice this is a table where the intervals are not the same from x value to x value. It's getting closer and closer and closer to 2, which is that idea of a limit. So I'm going to fill in the info that we got here. So 0.204, 0.200, 0.200, and then 0.200. So what this does is it really squeezes towards that value of 2. And when I look at what I've got on those 2 to the side of 2, and really they're very close to the x value of 2, I see that the y value is getting very, very close to 0.2. So it's a little less than 0.2 on the left. It's a little, I'm sorry, it's a little greater than 0.2 on the left, a little less on the right. But the table tells us, hey, and we're going to write this real carefully, the limit as x approaches 2 for the function x minus 2 over x squared plus x minus 6 equals 0.2. And that is my final answer. So just to recap, we started with a table and a graph so we could see what's the hang up. Why can't we just go ahead and put 2 into the function? We also saw in the equation that gave an indeterminate form 0 over 0. And then our strategy for actually finding the limit, even within those challenges and restrictions, was this horizontal table where I take values that are very, very close to 2 and use that to estimate, hey, what should that limit be? Well, let's take a look at one more example for this segment. So here again, I want to evaluate the limit as x approaches, in this case, -1 for the function 2x plus 2 over absolute value of x plus 1. So we'll start again by treating this as a function. So really we're going to think this is f of x equals 2x plus 2 over absolute value of x plus 1. And we're going to graph it. We're going to use our table. We should see why we can't use direct substitution again. So if I were to calculate f at -1, so I'm just putting that limit value in the function. So I'm just going to replace any x's with that value of -1. So 2 times -1 plus 2 over absolute value of -1 plus 1. So for our numerator, 2 times -1 is -2, plus 2 is 0. What am I going to get for denominator? Absolute value of 0. And how far away is 0 from 0? 0. So again, we're running into that same division by 0, which is undefined. It's an indeterminate form. So we again are running into that same problem. I can't use direct substitution. So let's look at our graph. I'm going to create the coordinate plane and the table so we can see what's going on graphically with this function. And let's center around -1. So I know that's where we got this undefined value based on our direct substitution, but let's catch some of these other points by, again, heading to our Desmos graphing calculator. So again, I'm just going to type that in, f at x equals, for my numerator, I had 2x plus 2. Put that in parentheses so that it hangs together as a numerator. And then you can do different things for absolute value. The fastest is to type ABS, parentheses, and then I'm going to put x plus 1, close parentheses, enter. So definitely we've got something strange happening here. So in my, like to the left of this undefined term at -1, I have a straight line at -2 going forever. To the right of the undefined value at x equals -2, I have a straight line at +2 going together. In fact, if I made a table, I wouldn't have to do a lot, because you see, let me add one more value there, -3. It shows that constant value. Now, let's record this table. So again, I'm going to just go to -4. But everything to the left of -1 is -2. Everything to the right is +2. So let's go back. That gives us the information we need from the graphing calculator. So it looks like I don't have to do a lot of calculation. Everything to the left has an output of -2, whereas everything to the right has an output of +2. Let's graph that. So at -1, we begin to the left. And we'll put an open circle there because really that value at -1 is undefined. Same above. Now, for this example, I don't really need to go back to Desmos to get that real specific calculator, or I'm sorry, table, because what I'm seeing right here gives me enough information. So I do want to take this to a horizontal table, and I'll place -1, that limit value. So you always put your limit value in the center, and we're going to go -1.001, -1.01, -1.1. On the right, we'll go -0.999, -0.99, -0.9. Now, if this had been a function with curves around that value of -1, the undefined value, I would definitely want to get specific numbers. But since this just is a horizontal line on the left, same horizontal line shifted up on the right, I know that all of these on the left are going to be -2. Everything on the right is +2. And when I compare these two that are so close to -1, I see that they are not equal. The left-hand limit does not equal the right-hand limit. Now, when we get that situation, what we claim is that the limit of the function as x gets close to -1 does not exist. So let's write that carefully. Limit as x approaches -1. And what we're claiming for this, and really for all limit problems, is that it's the limit as x gets close to -1 from the left and from the right. It's a two-sided limit of the function 2x plus 2 over absolute value of x plus 1 does not exist. Now, we've got this instruction. If the limit does not exist, give a reason why it does not. So one way that we could write the reason that this limit does not exist is because the limit, we're going to write this mathematically, as x approaches -1 from the left. So if I put a little negative sign there as a superscript to the limit value, means coming from the left, equals -2, which does not equal 2, which is the limit as x approaches -1 from the right. And that will suffice for our answer for what's the limit? It does not exist. And our reasoning for that is that the left-hand value of the limit does not equal the right-hand value of the limit. Okay, so I'm going to pause right there. We do have 2 more examples to look at, but I want to give you a chance to practice with some of your questions that you're working on. So let's take a short break, and then we'll come back with our final 2 examples.